Hi, today we'll be talking about defects and characterization methods. That's chapter 4 in your book, and some characterization part was covered in chapter 3, so it's going to be a combination. All right, so far we made the introduction. We talked about what a material science is, then we talked about two atom interactions after defining, of course, the atomic structure. Then we brought millions of them together and tried to reason out why they stack up in a certain order and what are the type of orders out there, the structures and the crystal structures, and we did some calculations on them. Today, we're moving away from that ideal world to the real world. Just like anyone else, like a person, nothing is perfect. So there are some imperfections and defects in the materials that is present in those perfect looking crystal domains. Doesn't have to be monocrystalline. Even in the polycrystalline materials, within those perfect crystal domains, we have some imperfections. In other words, a disorder or imperfection or defects in the order of these atoms stacking order. So we'll talk about those today. All right, so what type of defects out there and how can we characterize them? It's an easy way to characterize a defect is a dimension. There's going to be zero-dimensional, no-dimension defects. We're going to call them point defects. There will be one-dimensional, two-dimensional, and three-dimensional. The difference between them is the way we define the defect. For example, if I want to define a vector in space, of course, it is a line, so it's a one dimension, and I have to address a length, right, and two initiation and endpoints to it. If a defect is zero-dimensional, that means it's a point in space. So therefore, we call that a point defect. What kind of point defects out there? What kind of one-dimensional defects? Or what kind of defects out there two-dimension that we can define in two axes, or like a surface defects, right? Or what kind of three-dimensional defects out there? That's what we're going to analyze today. Well, we're going to do a lot of picture hunt. You probably play that game. So just you take a look at the two images that looks like almost the same, but if you look closely and then if you compare those two images, you can easily detect a difference between them. For example, for this pelican here, right at the tip of his nose, there is this black part is missing, so there you go, that's the difference between them. Everything else looks the same and perfect, right? So we're going to do a picture hunt for the materials atomic stacking in upcoming slides. Let's start talking about zero-dimensional defects, point defects. So let's do the first picture hunt. If you look at the left-hand side atomic stacking, it's perfect, right? Right here, everything comes in order, in equal separation, and all atoms are placed in their lattice points. But if you look at the right-hand side, this image here, well, what is the difference? The difference is one atom is missing here. So that point, that atom missing there is called a vacancy. Okay? So that's one type of zero-dimensional defect. Let's do another picture hunt. So this is perfect crystal, perfect ordering, but when we're looking at the right-hand side, there is some imperfection, some defect. Well, that's that little red guy stuck in between these two normal lattice sites that is making up this mother phase. So within that mother phase, I have an atom in between those lattice points. So that in between lattice points is called the interstitial site. Okay? Let me make a very important comment. Defects are not always a bad thing. Imperfections are the things for both people and for the material world, beautifying things a lot more. So this specific interstitial atom, although it looks like a disorder, although it looks like something foreign and something disturbing this perfect harmony here, it brings a lot of positivity and positive properties to materials sometimes, okay, in certain cases. So sometimes you want to get rid of them, sometimes you intentionally put in a certain order, okay? So what have we seen so far? Is a point defect, a vacancy, a lack of atom. Let me write that down. It's a lack of atom in its original lattice point. And also, for an atom, in between the interstitial sites, right? So in between those lattice sites, that's called the interstitial site. Let's do another picture hunt. This time, the difference between this beautiful, perfect picture, perfect crystal, there's a defect here. Where? It's right here, right in between, again, the lattice sites, again, interstitial atom, but this time it's not a foreign atom, it is self-interstitial, okay? So the atom couldn't find its place as a lattice site, it just squeezed itself in between the interstitial sites, so in between the lattice, original lattice of the crystal structure. Let's do another one, another picture hunt. This time we have this green atom that placed itself, substituted the original lattice point. So we have a foreign atom, which is a green one, right? Substituting the original lattice point. Well, this is again an impurity. It's a disorder in that ordered structure, and it's still called defect. But for example, alloying works with this principle, okay, or with interstitial principle, right? You add a foreign atom, it either goes to its original lattice size and substitute that atom. Substitution is a word, of course, for can use for anything, but for the materials world, it is the substituting original lattice point, right? But it can also happen with the foreign addition of an atom. For example, iron, carbon, and steel. Carbon goes to the interstitial sites and place itself. What do? You alloy iron matrix with carbon. Then you create this beautiful steel structure we're going to see in detail in phase diagrams, right? Well, for example, this foreign atom here substituted the original atom can also be part of alloying. That all has to do with relative atomic radiuses. We're going to see the rules of it. Okay. So to summarize the type of zero-dimensional defects, we can either have a vacancy, we can either have or have an interstitial atom, or we can have a substitutional atom. Okay. A substitutional atom can be either a little larger or a little smaller than the original atomic radiuses. So what you see here on this picture is the crystal's response to that defect. In the case of a vacancy, since there is no atom holding all this lattice structure, then there is the dimension of the stress is toward it. Okay. So the crystal collapses into those vacant sites. So there is this force inclined toward those empty spots. On the other hand, if we have an interstitial atom in between the lattice points, that actually exerts a force outward, right? So compressive or tensile strain is created around these zero-dimensional defects. Similarly, based on the atomic size in the substitutional defects, we either have toward that defect or outward from that defect, hence compressive or tensile strain created in the material. But the question is, if we mentioned that if this perfect crystal is the lowest atomic energy configuration? Well, the system, everything in nature, tries to lower its energy, right? So all systems goes toward lower energy. For material system, the energy of a system is defined as the Gibbs-free energy. You're going to use these Gibbs-free energy terms, especially in the upcoming phase section, and also when we're defining some other structural material quantities and qualities, right? So this energy, Gibbs-free energy, has an internal energy, enthalpy indeed, and some entropy terms enrolled in it. If a material system wants to lower its energy and having that perfect interatomic spacing, accomplishing that energy minima, so why would a system want to go to a position or state where it has some vacancies in it, for example, as a zero-dimensional defect? Well, it lies in that Gibbs-free energy terms. In the case of the internal energy, it's higher when you create these number of vacancies inside, the defects inside the material. You increase the internal energy of the system. And also keep it in mind, we have a solid system. In the solid system, this pressure and volume with change in temperature or with increase in the vacancies is ignorable, that change. This internal energy, while it's increasing, but my temperature is also increasing here, the T term, as well as the entropy term is increasing. So energy term being the positive, still increasing, if this T times S, temperature times the entropy term, increase ever more, even more than that term, then what happens? Gibbs-free energy is lowered, a lot more negative. So the system prefers to form these vacancies. But how does a vacancy form as I increase the temperature, for example? Let's say I have a perfect crystal to start from, and I'm raising the temperature. First thing, so one of the surface atoms moves out to the surface and rebonds there. So that vacancy diffuses. After this point, it's all mass transport inside the solid material. That vacancy diffuses in an opposite direction of atomic movement. So I can write down, if the vacancy movements, let me write down right on where it's happening. If the vacancy is moving downward, vacancy movement, atoms are moving opposite direction. Atoms movement. So we are moving the atoms, and whatever is the lack of atom position, hollowness there, that vacant position, vacancy, is moving in the opposite direction. So then my vacancies are created in the bulk inside the material, first by initiated the surface atom movement. That diffusion concept is introduced in chapter 5, right after this chapter 4, but we're not going to be covering it within this lecture series. Let's calculate how many vacancies I can create based on the temperature. Well, it turns out the number of vacancies that you can create in a bulk material is exponentially related with the temperature. So that's called the exponential relation is Arrhenius law, right? So this Q value, which is the energy required to activate the vacancies, can be measured from experimentation, okay? What the terms are, this relationship between number of vacancy you created with respect to the temperature, exponential relation, includes these terms. First of all, I need to have certain number of atom sites. Well, let me see. I can show it here. In this specific bulk of atom, how many atoms do I have? I can count from left to right and to bottom the number of atomic centers. That's the number of lattice points, available points where you can create vacancies. That's the total number of sites where a vacancy can exist. So, therefore, N is being the total number of atomic sites in the material, and NV is the number of vacant sites that you can create inside the material based on the temperature. So that's the relation. There needs to be some certain activation energy you have to give to the system to create these vacancies, of course, and it is exponentially related. There's a negative sign in front of it, don't forget. Although it is in the denominator, it is negatively related. So there's an exponential increase in the vacancy, number of vacancy in the total number of atomic sites in any given system. Let's make an example of it. This is from your book. The book is asking, the question in the book is asking, calculate the equilibrium number of vacancies per cubic meter for copper at 1000 degrees C. The energy for vacancy formation is 0.9 electron. That's a Q, by the way. That's the formation energy for the vacancy. 0.9 electron volts per atom. It could have been given as joules, by the way. And in the case of a joules, if it's given, then you have to use this Boltzmann constant K as this value. If it's given electron volts, you should use this value. But in either of the cases, the temperature, you have to use Kelvin, okay? 1000 degrees C. How many vacancies I can create in a copper bulk at 1000 degrees C? That's the question. There are other variables are given for us to calculate number of sites, for example, in copper, and so on. Another important information is copper is an FCC structure. Why do I need that information? Because to calculate the number of atomic sites, I'm going to use two different methods, okay? One method, I'm going to go from the unit cell. The other method, I'm going to go from the density calculations, okay? It is FCC, and also what else is given? The lattice parameter of the FCC copper cell is given as 3.61 10 to the minus 8 centimeter. Okay. All right. So let's do calculation on the right hand side and left hand side separately. Let's first calculate the number of available sites for the vacancy formation. If I go from the FCC point of view, if you remember the FCC structure, how many atoms did I have in FCC? I had 4 corner atoms making up one atom, if you remember, right? One from corner. And I had face centers holding only half of an atom. How many face centers I had? 6 times half. So there are 4 atoms in a FCC cell, right? If there are 4 atoms in a cell, and if I know the volume of that cell, the cube here, the volume of that cube, what do I get? I get atoms per either centimeter cube or meter cube value. That's the value that I want to get at anyway. For a given volume, bulk, how many atoms do I have? How many atom sites do I have? That's what I want to calculate. I can either go from that unit cell discussion, or I'll show you we can go from the density discussion. Let's do this first. If there are 4 atoms in a unit cell, if I divide that into the volume of the cube, which is the one side the lattice parameter is given, I get 8.47 10 to the power 28 atoms per meter cube. If I take a meter by meter by meter copper volume, there are this many atom sites in there. That's a huge number. Okay, 10 to the power 28 is, what is that? 10 to the power 9 times 10 to the power 9 times 10 to the power 9 times 10. Billion times, billion times, billion times 10. Okay, it's a lot of atoms per meter cube. Okay, so what else we can do? We can calculate it from the atomic weight, which is given in the question as 63.5 grams per mole, and also the density. What is a density? Density is m over v, right? So what is the volume then? If you can calculate the, hold on, m over rho over m 1 over v, yeah. So if I want to calculate how many atoms per meter cube is, so it is going to be equal to 1 over V will be atoms per meter cube, if volume is. So that's going to be equal to rho over m. But I also have to calculate with the Avogadro's number to get that atoms per mole. Why? Because this is grams per mole, 8.4 grams per centimeter cube, sorry. And how many grams per mole as a weight do I have? 63.5 grams per mole. And if I divide them to each other, what do I get? Moles per centimeter cube, right? So if I multiply that with the Avogadro's number, which is atoms per mole, moles times centimeter over centimeter cube times atoms per mole gives me atoms per centimeter cube or meter cube. So let's plug in everything into that equation. Avogadro's number times the rho times the conversion factor from centimeter cube to meter cube over the weight gives me 8 times 10 to the power 28 atoms per meter cube. If you compare these two quantities, these two quantities are extremely close to each other. They're both on the order of 10 to the power 28. They're both 8 times. For the LCC unicell approach, we had 0.47 times more error. That's acceptable. Okay, so now I know the total number of available atomic sites. How can I calculate the number of vacancies? Well, the vacancies were equal to those sites times the exponential activation energy over Boltzmann constant times the temperature. Although the question is asking the copper's equilibrium number of vacancies at 1000 degrees C, I'd like to show you first what is the number of vacancy of copper at room temperature at 25 degrees C. Well, if I plug in these numbers, converting 25 degrees C to 298 Kelvin, I obtain 4 times 8 times 10 to the power 10 to the power 13 vacancies. Well, this is not a lot. If there are available sites on the order of 10 to the power 28, if I divide that into 10 to the power 13, what do I get? 1 over 10 to the power 15. So billion times million, for every billion times million atom, I only have 1 vacancy at room temperature. That's what it means. But if I raise the temperature, as we said, it's going exponential, right? As I raise the temperature, as I get close to the melting temperature of copper, look, the melting temperature of copper is given as 1085 degrees C. Okay, so we are 85 degrees just below that melting temperature. Okay, so we're at that temperature, 1000 degrees C, which is equal to what? 1273 Kelvin. And if I plug everything in, what do I obtain? I obtain 2.2 times 10 to the power 25 vacancies per meter cube. Well, if there were available sites on the order of 10 to the power 28, and if I divide that into 10 to the power 25, what do I obtain? 1 over 1000. It was billion times million 10 to the power 15 atoms held 1 vacancy at room temperature. On the other hand, as I raise the temperature to 1000 degrees C, what happened? For every 1000 copper atom, I had 1 vacancy. So I had 10 to the power 12 times more vacancies introduced in the material as I went up to 1000 degrees C. So temperature is super important. All right, so interstitial or substitutional solution. So we've seen that those other than vacancy, we can have a point defect either interstitially positioned or as substituting the original mother atoms, mother phase. So it depends on 4 things it's given here. 1, it depends on atomic size factor. So If the size is in between plus or minus 15%, then what's going to happen? It'll most likely find those interstitial sites, or then if I have larger ratio, then it might go into that solid solubility, substitutional solid solubility end. If you want to have the solid solubility of a secondary atom addition to the mother crystal matrix, then to have the highest solubility, both crystal structures got to be the same. If I have an FCC aluminum, for example, and FCC copper I add into it, there's more likelihood of these two atoms to mix, of course, if the other three rules are fulfilled, right? So what else? Electronegativity. If you pick two elements from the two other ends of the spectrum of the periodic table, then they're more likely to form intermetallics instead of mixing and creating that solution. Okay, so they will form intermetallic compound instead of a substitutional solid solution. Okay, so let's repeat. Your atomic radiuses should be similar to have that solid solubility, a substitutional solid solubility, at least plus or minus 15%, right? And your crystal structures got to match, right? And then you need to have similar electronegativities. One last thing, all other factors are being equal or similar, a metal will have more of a tendency to dissolve another metal of higher valency than of a lower valency. Okay? Having a higher valency is a preference for solubility. By the way, these are, as I said, named after defects, imperfections, but let me show you one benefit of this defects, having this either substitutional or interstitial. First discussion was alloying. Alloying, by the way, is a fraction amount alloying. You can add a fraction amount of other metal part or element B into element A, and you mix them at a certain fraction. High percentages. So you can count, for example, I add metal B to metal A, 1%, 5%, 30%, or 50%. That is called alloying. On the other hand, for semiconductors, we're going to see in the electrical properties section, you need to have doping. Doping and alloying are two different things. They're two similar things, but they're named after differently because of the amount you put in. In the case of a doping, you're not putting the secondary element in the fraction amount. You put in part per million to maybe 1%, up to few percent. So that's called part per million, ppm levels, which means for every million atom you put one B atom. On the other hand, for the alloying, for 80 B atom, you can put 20 B A atom. So every 5 B, you can put 1 A, like it's fractional. In the case of a doping, other than alloying, you put so little amount, okay? So to make a semiconductor, you take a semiconductor, silicon for example, and you want to make it a conducting material out of it. So what do? Normally, in a silicon structure, as you see in the blow-up, has 4 valences, right? And they're shared by the 4 other silicon atoms surrounding each electron in each valence is shared by that each silicon atom surrounding that covalently bonded surrounding, right? So if you take a phosphorus atom, if you look at the periodic table, it's right next to silicon, so there's not much of electronegativity difference. The atomic radiuses are similar, right? So almost all of those rules are accepted here. But you substitute, they don't go into interstitial sites, right? They substitute the silicon atom. To have an interstitial positioning, you need to have a significant amount of difference in between the atomic radiuses. So you substituted the silicon atom with phosphorus. Look what happens. Since phosphorus atoms have one extra electron in its valence, okay, it forms that covalent bond with the silicon, substituting that silicon atom, but there's one extra electron here that can be utilized as a free electron in the conduction band, right? So, is this a defect? It's definitely a defect. So you can do that picture hunt for that perfect silicon structure and that phosphorus doped silicon structure, and you see there is this imperfection and disorder in that stacking of silicon. So you substituted one silicon atom with phosphorus, created an intentional defect to improve upon the electrical properties. Alright, so it's a double-edged sword. So you can either make good for your material by introducing these defects, or you can do bad. So you have to know what a defect does to your material. First of all, you have to know what a defect is, and then you have to know what that defect does to your structure. Then you can play with it. Okay. Let's move on to one-dimensional defects, line defects, and let's play that picture hunt game here as well. I have perfect stacking of atoms here, but I have the same perfect stacking of atoms, except I have a missing line of atoms this time. Look, vacancies stacked up one after another, those lack of atoms, created those zero-dimensional quantities, those points stacked up one after another, that created a one-dimensional defect. Similarly, for two-dimensional defects, one-dimensional defects can stack up one after another, creating that surface. We'll see that, right? Or those surfaces stack up one after another, what do they create? A bulk and volume defects, three-dimensional defects, okay? So, well, in case you didn't pay attention, there is two regions to that crystal stacking. You can take a look at here, it's still perfect stacking here, but where that defect is, at the bottom. So there is a good health and defected health. The plane that separates that perfect stacking and that imperfect stacking is called the slip plane for the dislocation line given. So that missing line of atoms that created that dislocation, which is one-dimensional defect, is called the dislocation line. And just right above that slip plane that separates those two domains, perfect, imperfect, right? And above that slip plane, we have an extra half plane compared to that bottom portion of the slip plane. Normally, dislocation is the reason, as I've been telling you, one of the core reasons indeed for plastic deformation. So we introduced the slip systems in the previous lecture, lecture 3, crystal structures. And we said the slip plane is the plane along which dislocation glides through. Let's take a look at what is that glide mechanism. Well, that glide mechanism is exactly, you break the bond here in between these, the complete line of atoms breaks the bond and moves next door, just like that vacancy formation movement. If the atoms move on the left-hand side, then where does the dislocation line will move? In the opposite direction, right? So, but how do they move? You have to apply a certain force to it, right? If your shear force, that's the stress that you're applying to that shear stress, that opposing forces to each other, is perpendicular to that edge, the dislocation line. Look, this is the movement of my dislocation line. It's in this, it's got to be moved perpendicular to its formation. So the movement of that dislocation line can only be achieved perpendicular to it. That dislocation is called edge dislocation. There's other type of dislocations as well. We'll talk about them. But this edge dislocation movement occurs on that slip plane that separates perfect, imperfect regions. And the direction through which this is gliding is called the slip direction. So that slip systems that I've shown you for FCC and BCC in the crystal structure for mostly dense packed planes, right? That was the definition, mostly dense packed planes. And what? Directions, again, mostly dense directions. Mostly dense directions. Combination of these two is called slip system, right? So in the case of this dislocation moment, the plane through which it is gliding, that plane separating perfect imperfect regions, is called slip plane, and the direction at which it's moving is called the slip direction. So that system is called the slip system. So to have that movement, of course, we have to apply stress in the slip direction. Okay. Of course, even if you apply in different directions, it will prefer to move on that slip direction. Okay. So that as we apply that force against each other from top and bottom, right? As the material experiences, what's going to happen? The bonding between the neighboring line of atoms will break and they'll reform, and the dislocation mode. And it happened one more time, it happened one more time, just like this caterpillar movement you see there. So let me revisit that slip systems. The slip systems are defined as mostly dense packed planes and directions, especially for FCC, which is a close packed structure. All these slip systems are active. But in BCC and HCP, for example, yes, there are slip systems, but they need to be active. They're not active. They're not mostly dense as packed as FCC metals. They sometimes need a little thermal activation. So let's take a look at what are the slip systems again. In FCC structure, it was almost 90% packed 111 plane, and the vectors surrounding it 011 planes or 110 directions. Sorry, combination of these two makes my slip systems in an FCC. In case of a BCC, the mostly dense packed plane is the body diagonal, but it's not as packed as that 111 plane. And these are the directions, this is the directions, 111 directions, in combination with 111, and also other irregular planes in between, also containing that 111 direction, making up 48 slip systems, but it is not as active as the FCC systems. Okay. So what's really happening overall in the bulk? I have these dislocations in the material, and as I apply a force to the material, which means I'm applying a tensile force, that tensile force is converted into that shear, as you can see. So if the plane that is preferred, that slip plane, is at this angle, apart from that your applied load, then the material will create these glides one over each other, right? So they're going to glide as the dislocations move along those slip planes. So that glide of those slip planes over over each other creates an overall deformation in the material. If you lack of these slip systems, you can create this plastic deformation mechanism. This is why metals have these plastic deformation mechanisms, because of those presence of those defects along with the slip system, dense packing, right? All right, so let's keep going on. Let's talk about still the dislocations we're talking about, specifically in edge dislocation. How do we define an edge dislocation? Edge dislocation is the dislocation that it's Berger's vector. Look, I'm introducing a new jargon. Berger's vector is perpendicular to its dislocation line. What is the Berger's vector? It is the direction toward which these dislocations move, the direction that I'm applying the shear force, right? Dislocation line. That's the definition of an edge dislocation. They're perpendicular, that they create an edge, the dislocation line and the the direction of the shear force, right? So if you look at here, since we have an extra plane on top of that, if this is my slip plane, above the slip plane I have an extra row of atoms, so that creates that compression. That's extra atoms. On the other hand, where I have these dislocation lines, there is below that slip plane I have that tension. Okay, so this compression and tension will be very important when we're talking about the strengthening mechanisms in chapter 7 after we talk about the mechanical properties. Just keep in mind. Okay, so now we understand what the edge dislocation is and how it looks like. Let's take a look at how to find the Berger vector of it. Well, it's very easy. First of all, you need to identify where your dislocation is. So it's obvious my dislocation is the core of the dislocation, where it's originated. Above this slip plane, I don't have any imperfection, any disorder in the stacking, but below I have that disordered or dislocation originated domain. So therefore, my dislocation core center is right where my slip plane and intersection of that slip plane with the dislocation line. This is where my dislocation core is. Intersection of that slip plane with the dislocation line. Around that core, I will be making a full circular trip after identifying that core. What kind of circular trip? If those lattices, each lattice is a one step, I'm going to take equal number of steps to right, to south, then to west, then to north again. Left, down, right, down, left, up. So as I do that complete turnaround, of course I'm not going to end up at the same place. So whatever is the lacking step, either one step, two step, whatever, then I'm going to find that Berger's vector drawing where I initiated, where I ended as a vector. Let's do that. My Berger's vector is going to be drawn like this. You can pick, by the way, any point around that dislocation center, that core. You can pick here as well, or you can pick close to it, whichever you want to. But as long as you make your full trip around, circular trip, you'll find in the clockwise direction. Well, we pick this point, and from that point I go 1, 2, 3, 4, 5. I do the same down. 1, 2, 3, 4, 5. I do to the left. 1, 2, 3, 4, 5. And I do it up. 1, 2, 3, 4, 5. Of course, as expected, I did not end where I started. Why? Because there is a dislocation. There is a one-step difference between the above and below domains, right? So that tells me the direction of my Berger's vector. That's my Berger's vector, which is the direction through which these shear forces felt on that dislocation line. There's also another type of dislocation, which is called the screw dislocation. In the case of the screw dislocation, my dislocation line this time is parallel to my Berger's vector. The shear that is felt, direction of that shear that is felt, is parallel to my dislocation line. So if you take a look at this bulk here, this time it's a shear that is tearing this bulk away from each other, right? So I have a dislocation line right here. This is the top view, by the way. Top transparent view. So this is my dislocation line. This red guy here. That's where it's originated, right? Why? Because the dislocation above that, I have perfect, and here there is this still moved or moved or dislocated bulk, right? So as I apply the shear force more, so this the direction of the force, right? I'm tearing it. As I apply that force more, what is going to happen? My dislocation line will move up, then move up, then move up, then move up. That's the way it's propagating. But while it's propagating, the line and the applied forces, the felt shear force, is parallel to each other. How do I determine the dislocation line in this case? It's very easy. I do the same thing. After I identify where my dislocation line, the core of that movement is, I make a full turn around it. So I start from here, 1, 2, 3, 4. You can start indeed if you would like, like 1, 2, 3, 4, 1, 2, 3, 4. So there are 8 lattices in each direction I have to go. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. If there was no step as such here, that will be perfect turnaround and complete through. But there is a lag in between these 2 points that actually defines my burger vector. While I'm completing my turnaround, that's the missing vector preventing me to complete the or tie the ends. Okay. I can also have a mixed dislocation in a material. It's a very good example here. For example, on this face, I have a screw component, and I have an edge component. So as I move the screw dislocation toward that line away, then as it's moved, this screw dislocation will eventually change into a edge dislocation on this side, terminated into a edge dislocation. So to wrap up the one-dimensional defects, there are edge defects, there is edge dislocations, screw dislocations, which is Burger's vector parallel, and mixed dislocations. It's a mixed Burger vector. How do we increase the number of defects in one-dimensional defects? There are 3 different ways of doing that. One is by plastic deformation. Of course, as I apply force and heavily deform the material, it creates its own deformation mechanism, its own dislocations in the domains. I can put some impurity atoms, or I can increase the temperature. Creating those vacancies will also create the lining up those vacancies, creating new dislocations in the domains. Okay. So let's talk about 2-dimensional defects. So that's called area defects, of course. Why? Because I can define them with 2 axes and 2 dimensions. And just like line defects made up from the 0-dimensional point defects, these defects are also made up of 1-dimensional defect stacking up. So in the case of 2-dimensional defects, we'll talk, since it's a surface defect, a stacking fault can be counted as a 2-dimensional defect. Why? We've seen it in the crystal structures. HCP and BCC was stacking in AB order, if you remember. A planes, then B planes, A planes, then B planes. On the other hand, for FCC, the stacking was ABC, ABC. And this example here just shows very well. If there is some imperfection in that stacking order, like, for example, instead of having ABC, 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 I have, again, I'm making a picture hunt, right? What is different between these 2 guys? I have ABC, AB, oh my God, there's no C plane and there's an A plane getting in between, right? So that specific missing plane, or just instead of no C plane present here, is a stacking fault. Fault in a stacking, that's called a two-dimensional defect. It's an imperfection in two dimension, right? Another defect, we also talked about this in the crystal structures. There are polycrystalline materials, and the reason for forming those polycrystalline materials was the nucleation and growth mechanism coming from liquid to solid state, if you remember. There were multiple regions where you create these nuclei, they consumed the liquid matrix, and they created different single crystal domains. But these single crystal domains in the end are not perfectly lined up, as you see here. So this domain, these atoms are perfectly ordered, but the neighboring domain, the neighboring grain, these atoms are also perfectly stacked up in themselves, but with respect to each other, these domains have a certain orientation. They're not continuing on that stacking on the neighboring region. So due to that misalignment, we have a boundary, an invisible boundary that is separating these single crystal domains, which we call grains. And in between those grains, that invisible boundary, that surface, is called the grain boundary. It's just like a pomegranate, and there's membranes that is separating each pomegranate grains. That is a very good example from our daily life. So I have to make a note, very important note here. If I have a single crystal domain, that doesn't mean it's perfect. It's perfectly atomically stacked. Within those domains, of course, we can have either dislocations or vacancies or impurities or stacking faults. They are the inhabitants of those single crystal domains. Okay, those defects are still present in those domains. So having a grain boundary is an additional surface defects in between those domains. And also, let me introduce here another important parenthesis. Please think about, if I have dislocations in these single crystal domains, think about if I want to move that dislocation, and while that dislocation is actually traveling through those slip systems, they move and move and move and move, and what happens? They come to this grain boundary interface. If these atoms were continuing on along the same directions, the dislocation would keep going on its movement unless there was an imperfection, some other atom in front of it. Let's say there's no impurity or secondary atom, and they're just like moving freely, right? Once this dislocation comes to this interface, she knows that she has to change a direction. So it requires an extra energy. So therefore, having grain boundaries, more grain boundaries, smaller domains, more grain boundaries, more polycrystalline material, harder for these dislocations to move, then what happens? Less of a plastic deformation, so there is more of a resistance in the material, creating strength. So if you look at that stress-strain curve, you'll see in the mechanical properties higher strength. And you see in chapter 7 in strengthening mechanisms, this is one of the ways to strengthen the material. So how do we form these single crystal domains? We mentioned that, of course, while we're cooling the material, if I cool really fast, if I don't give sufficient time to the system to equilibrate to its thermodynamic equilibrium, to find its minimum energy points, these atoms, right? Then what did I create? I created no long-range order, no long-range atomic stacking order, amorphous material. I can totally control how polycrystalline my material is going to be. Is it going to be single crystal or is it going to be amorphous by the processing variables? If I increase the rate at which it's cooling, it's more likely to form an amorphous material. Why? You don't give sufficient time for the atoms to find their energy minimum positions. But if you cool slowly, give enough time, you can either have this or this. What makes that difference mono or polycrystalline mostly is the environment that you're creating or preparing for this crystalline to form. Is it going to be homogeneous or heterogeneous nucleation? What is it going to prefer? What kind of parameters you're going to control there? But in the polycrystalline, how big a crystalline domains is going to be is also determined by, can be determined by how fast you cool, or also is there any impurities or contamination in the materials, also determines the polycrystallinity of the material. So as we said, if there's long range order, if you look over the material and like hundreds of atoms having the same stacking order, a perfect stacking, having that order in 3 dimension, there is a long range order, and that's crystal. But in the case of amorphous materials, we don't definitely have a long range order. But sometimes there can be some short range orders for few atoms. You can see some ordering in every few atoms, but in the overall look, there's no order in amorphous structures at all. Well, we're going to see today in the characterization methods. You can actually observe the atomic stacking, the position of these atoms in the material with a tool called transmission electron microscope. So this is a transmission electron microscope imaging of TEM image of an amorphous and a crystalline material. As you can see, these dark regions, dark points here are atom centers. On the other hand, here in the crystalline, as you can see, there is an order. It's making up an order here, right? You can observe in 2 dimension repeating order of the atoms. You can also detect vacancies or dislocations if you pay more attention to the details here. Okay, so average grain size in the polycrystalline materials are for metals are on the order of 0.15 to 0.24. So to observe the grain sizes, that's millimeter, by the way. This is about, by the way, if this is a millimeter, we can call 0.015 as 15 micrometer to 250 micrometer, maybe, right? Micron. It's no difference. It's not a problem. You can see those those size grains, not by naked eye, of course, unless it's 250 micron, or sometimes it's up to a millimeter. You can see large grain materials, of course. This is an average they're talking about. But if you want to see 15 micron grains, those single crystal regions, you have to look under the optical microscope. So we know how those domains are formed. It's a matter of how many nuclei sites I created while I'm processing and solidifying it. Of course, more number of those nuclei sites, the smaller the domains that I'm going to create, less number of nuclei you have, larger the crystal domains you'll have. And under the microscope, the misaligned grain boundaries will exactly look like this under the optical microscope. We'll see them in the characterization section. So how much misalignment those domains have with respect to each other determines the angle of the grain boundary. So if we have a certain alignment here, for example, for the upper domain here, and let's say I have another alignment here, a neighboring. So if I was to continue on that orientation, what would be the angle in between the new stacking versus old previous the domain, upper domain have? What is the angle difference between them? If that theta is in between 0 to 3 degrees, then it's called low angle grain boundary. If it's 3 degrees to 10 to 15 degrees, it's called medium angle grain boundary. And if that orientation misalignment is large, over 15 degrees, then it's called high angle grain boundary. Of course, higher the misorientation, higher the energy stored in the material system. Of course, that also affects the reactivity, chemical reactivity of the those boundaries in between those regions. What else it affects? Let's say if I have a dislocation moving in a certain domain and it comes to the end of that domain, to the grain boundary, if it needs a certain energy to move to the next alignment, higher the angle in between them, harder it is to move. So maybe overall you have a better strengthening output. So these grain boundaries can either be tilt or twist type. The tilt is, we've been taking a look at these grain boundaries as if it's a cross section, right? So these grain boundaries seen here, it's a cross section that you're looking at. They are actually, just like in the pomegranate example, are three-dimensional crystal domains. They're not just a flat plane that you see on the paper. We just cut through and we take a look at the planar view, but they do have a three-dimensional quantity, right? It's not only planar quantity. So these three-dimensional domains can be misaligned with respect to each other, we said, right? We talked about the misalignment. But if they're misaligned, that theta is creating this misalignment, creating an edge dislocation in between them, a dislocation line that is edge character to it. In other words, two domains are just tilted with respect to each other, then it's made up of edge dislocations. And if those two domains are not tilted but twisted with respect to each other, then it is shown here perfectly. They still have a certain misalignment with respect to each other, but in what orientation, what orientation is the right word, what orientation they actually do have that theta angle separation determines what kind of boundary it is, what kind of dislocations it is made up of, and what kind of boundary it is. It can be tilt by edge dislocations or twist by means of screw dislocations, okay? There's another type of boundary, a special type of grain boundary. It's called a twin boundary. A twin boundary occurs when there is a lack of plasticity in the material and when you're applying a force around a certain mirror atomic plane, the whole crystal shifts. So after that shift, if you look at that plane above and below, if it looks like a perfect mirror image of each other, then it's called a coherent twin boundary. Is this a misperfection? Yes, it is a misperfection. It is a defect, right? Because it's a disorder in the atomic stacking. So that plane here is a twin boundary. Here, this is twin boundary, and that's a coherent twin boundary. But around that mirror plane, if it's not continuous, it's not perfect mirror, there are discontinuities, the lineup of these atoms are not perfectly lined up and it's not perfect mirror image, it's called incoherent twin. As you may guess, incoherent twin has a higher energy compared with the coherent twin boundary. Let's take a look at it. I think in the strengthening mechanisms you're going to see the deformation twinning phenomena. This is exactly what it looks like. So if there is a lack of slip systems and these lack of active slip systems along with the dislocations or the defects, right? Then the materials still deform, but around these twin boundaries, repositioning the whole crystal around a certain plane that is called a twin boundary. In the case of a slip system, crystallographic orientation across the plane is the same, but in the case of a twin, it's reoriented. Atomic spacing in the case of a slip they have these multiples of atoms, but in the case of a twin deformation, we have less than an interatomic separation that occurs in twin. So you can actually see here the main difference, deformation by slip planes, slip systems versus the twin planes. Okay, so this is the last part. We're almost wrapping up and finishing up this defects chapter. Three-dimensional defect now we're going to talk about. These are the defects can be characterized with three axes, X, Y, Z. Whilst they're just like bulk and volume defects. It can either be some kind of inclusion in the material, or it can be crack, for example, or it can be a pore in a material. Okay, so all these three can be calculated with three-dimensional quantity. That concludes the defects section. Right now we're almost done with the basics that is making up the properties of the materials. We're slowly building up on it and just progressing toward those properties sections. But we're done with another milestone, defects, chapter 4. And after we talk about the characterization methods this week, we'll move on to phase, then to the properties. Thank you for listening. I'll see you in the next lecture.